Hey everyone, welcome to this explainer. Today, we're doing something I'm really excited about. We are going to take the math that usually just sits there perfectly flat in a textbook, and we're literally lifting it completely off the page. We're going to apply it to the real world, three-dimensional spaces that you and I live in, work in, and interact with every single day. Okay, let's dive into this. Here is our agenda for today. First, understanding 3D solids. Second, cuboids and cubes. Third, calculating practical costs. Fourth, slicing through cross-sections. And finally, the flow of liquids. All right, part one, understanding 3D solids. So let's ground ourselves with a few core definitions straight from the source. A solid is, well, it's simply anything that occupies space and has a definite shape. Simple enough, right? And once we have a solid, two fundamental properties emerge. First up is volume. Think of this as the internal capacity or the actual physical space that the solid takes up. The second is surface area. That's exactly what it sounds like. It's the total sum of the areas of all the outer surfaces wrapped around that solid, the whole shebang. Now, thinking about how geometry stacks this complexity reveals a pretty cool progression. In a one-dimensional world, a 1D figure only has length, like a simple line, which you measure by its perimeter. But add a second dimension, and we get a 2D figure with length and breadth. Now we can actually calculate an area. And when we finally step into our three-dimensional world, we add height. Length, breadth, and height all working together to turn a simple flat line into a massive object with actual volume. Moving on to part two, cuboids and cubes. And this brilliantly illustrates our starting point perfectly. Take a look at this standard cuboid. It is essentially just a rectangular solid. It has 6 faces, and every single one of those faces is a rectangle. You can clearly see those 3 dimensions we just talked about. You've got the length at the bottom, the breadth giving it depth, and the height giving it that vertical presence. Because a cuboid is such a predictable, uniform shape, the formulas to measure it are incredibly reliable. To find the volume, you just multiply length by breadth by height. Super easy. But look closely at the surface area formulas because there's a really important distinction here. Total surface area calculates all 6 faces, top, bottom, and all 4 sides. However, lateral surface area only calculates the 4 vertical walls. So, say you're painting a room, but you're skipping the floor and ceiling, that lateral surface area is the exact formula you're going to need. Now, what happens if you take a cuboid and you make the length, the breadth, and the height all perfectly equal to one another? Well, you get a cube. A cube is just a special relative of the cuboid where every single one of its 6 faces is a perfect square. And since all the edges are exactly the same unit, the volume formula simplifies beautifully. It's just the edge multiplied by itself 3 times, basically the edge cubed. Which brings us to part 3, calculating practical costs. So the crucial point is, why do we actually need to know these formulas? Well, because in the real world, materials cost money. Unless you're a mathematician, you probably aren't just measuring boxes for fun. The source material highlights what we can call the golden rule of commerce. Cost always equals the rate multiplied by the quantity. If you know how much material you need, and you know the unit cost, you can solve literally any real-world budget problem. To really anchor this abstract math into relatable, everyday life, the textbook gives us some great analogies. Just think about how we shop. We buy petrol by its volume, right? Paying a specific rate per liter. We buy a plot of land by its area, paying a rate per square meter. And we buy fabric or cloth by its length, paying a rate per meter. The math directly dictates the commerce. Whenever you're facing a problem involving the cost of something, you can reliably use a really straightforward 2-step process. Step 1, you do the geometry. Calculate the exact quantity you need by finding the volume or the surface area. Step 2, you do the commerce. Multiply that calculated quantity by the given rate to find your total final cost. Let's see how this scales up in the real world. Take a massive factory shed. In this scenario from the text, the shed has brick walls, an asbestos sheet roof, and it's 50 meters long. If the owners want to replace the roofing at 25 rupees per square meter, they can't just guess. They have to calculate the total surface area of those slanted roof panels and then multiply that by the rate. And you use the exact same process to figure out the cost of painting those giant exterior brick walls. Honestly, it's the geometry that makes project management possible. All right, part 4, slicing through cross-sections. Now, what's really interesting about this slide is the concept of a uniform cross-section. So a cross-section is the face you get when you make a cut straight through a solid, right perpendicular to its length. If you slice a block and every single slice gives you the exact same shape and size, no matter where you cut it along its length, that solid has a uniform cross-section. It's kind of like a perfectly unsliced loaf of sandwich bread. Having a uniform cross-section is incredibly helpful because it acts as a really powerful mathematical shortcut. Instead of doing a super complex 3D calculation, if a body has a uniform cross-section, its volume simply equals the area of that cross-section multiplied by its entire length. Just find the area of the front face, stretch it across the length, and boom, you have your volume. This shortcut is an absolute game changer for odd shapes. Let's look at this solid block featuring a trapezium-shaped cross-section. Calculating the volume of this normally would be a total headache. But because that trapezium face is uniform all the way through its 1 meter length, all we gotta do is calculate the area of that one single trapezium face and multiply it by the length. Complex math made beautifully simple. Let's move to part 5 and see how this builds into fluid dynamics, the flow of liquids. Imagine a pipe for a second. It's essentially just a long cylinder, a solid shape with a specific volume. But what happens when that volume doesn't just sit still? Like, how in the world do you calculate the volume of water when it is constantly rushing out of a pipe and never standing in one place? Well, the source gives us a brilliant adaptation of our cross-section shortcut. For liquids, the volume of water that flows in a unit of time equals the area of the cross-section multiplied by the speed of the flow. Did you catch what happened there? Because the water is actually moving, speed steps right in to replace length. To put into perspective just how powerful this is, the text walks us through a crazy calculation. Imagine a pipe with a tiny cross-section of just 5 square centimeters, but the water is rushing out at a speed of 30 centimeters every single second. By multiplying those together and scaling it up to just 1 minute, we find out this tiny pipe pumps out a massive 9,000 cubic centimeters of water. That is exactly 9 liters every 60 seconds. Pretty mind-blowing for such a small pipe, right? Okay. One final practical concept for you regarding water and solids. When a solid object, let's say a cube, is completely submerged into a liquid, it takes up space. The rule here is absolute. The volume of the water that is displaced, meaning the water that's forced to rise and overflow, is exactly equal to the volume of the solid you dropped in. It is a perfect one-to-one geometric trade-off. We've definitely covered a lot of ground today. From the basic definitions of 3D solids to cuboid formulas, calculating material costs, leveraging cross-sections, and even measuring flowing liquids. So I'll leave you with this. Next time you walk past a water pipe, step into a freshly painted room, or just stare at a packed warehouse, how will you measure the space? Because the math is right there, just waiting for you to use it. Thanks so much for joining me on this explainer, and keep exploring the dimensions around you.